Good day, everybody. So we learned that chemistry is the study of matter. The natural question to ask would be, what is matter? Matter is actually defined as anything that occupies space and has mass. For example, the noodle, air, water. But do remember, light is not matter. Light is actually a type of energy, which we will talk about later on in this chapter. One thing about matter is they might appear smooth and continuous, but actually it's not, because matter is actually ultimately composed of atoms. The structure of atoms will be one of the topics that we will talk about in later chapters. Today, we are actually able to see atoms using instruments that is called scanning tunneling microscope, STM. In this picture, you see the nickel atoms using STM, the scanning tunneling microscope technique. Anything can be classified into different groups. So let's classify matter first by its physical states. We know matter can be classified by physical states into a solid, a liquid, or a gas. So let's study some of the common properties of solid. For example, solid, they are close together. So because of this reason, they have a definite shape and definite volume over there. It's basically mostly incompressible. And for liquid, the molecules, they are actually free to move relative to one another. However, they are still close enough together. The shape, though, because they can move by each other with relative freedom, so they have indefinite shape. Actually, it takes the shape of that portion of that container. For the volume, though, it is definite. It's mostly incompressible. For gas, the molecules are mostly free to move by each other, so they are far apart. And the shape is indefinite, and it actually fills up the container. It takes the shape of the container, it also fills up the container. So the volume actually it's indefinite because it will change with the container. It is fitted in. So it's highly compressible. Matter can be classified by the physical states. Matter can also be classified according to its composition. When we do so, a matter can be classified either as a pure substance or a mixture. A pure substance is simply one substance that has its own definite and constant composition. Thus, it also has a distinct chemical property. In contrast, a mixture has a composition that is variable, so the chemical properties will change accordingly. So let's look at some examples. For example, a pure substance, you might have a table salt, which is NaCl. You might have water. Right? What about helium? Yep. Ozone, etc. We can further classify a pure substance into an element or a compound. So what is an element? An element, the original definition is it's just a pure substance that cannot be further broken down into simpler substance. But when you are given a question, you're not going to run a reaction and see if it breaks down further. A more practical definition would be an element is made of only one type of atoms. The key word is type. So for example, helium, apparently that's one type. All right. What about ozone? Ozone, it's an element, not a compound. Although you have three atoms combined together, but it's of the same type. Similarly, sulfur molecule, which is S8. You have 8 atoms, but I don't care because they are of the same type. So this is also an element, not a compound. So let's look at some examples of a compound. What about CO? When I write it, both are uppercases, which means you have a carbon and the oxygen. So this is carbon monoxide. You have two different elements combined. They are two different elements rather than one. So this is a compound. But if I write this differently, if I write a C uppercase and the O as the lowercase, this is actually an example of an element, not a compound. Because when you write the elemental symbol, all elemental symbols are either made of one or two letters, but only the first one, only the first one letter can be capital. If you see a capital letter, that means it must be a different element. But when you see one capital and one lowercase, that means this is actually one element or one different type of atom. So this is not a compound. It's an element. Oh. Let's look at some examples of a mixture. For example, you might have noodle soup, right? Yeah. What about sand? Apparently, you can see different substances inside, right? What is a homogeneous mixture? Homogeneous mixture, actually, when you look at composition, it's uniform, that's the key word, inside the whole sample. For example, you might have salt, water, okay? So you take a sample of salt water, and here and there, it will be exactly the same composition, same percentage, all right? What about heteromixture? Heterogeneous mixture. For example, you have the noodle soup. Some you can apparently see different places. They have different composition. Here you have the noodle. There you have the water, and then you have some other things as well. All right. Okay. Of course, you can come up with some other examples very easily. Let's go over the whole procedure about classification of matter. First, you look at the composition. See if it's changeable. If it's not changeable, if it's a definite composition, that means it's pure substance, or else it's a mixture. And an element is actually a pure substance that contains only one type of atom or atoms. A compound contains more than one type of atoms or elements. So for homogeneous mixture, it's uniform throughout the sample. And for heterogeneous mixture, it's not uniform throughout the sample. Let's look at some examples. Which of the following is a pure substance? Apparently, the correct answer is A. Sodium is a pure substance, and it is, more specifically, it is an element. Next example. Which of the following is an element? Sugar is a combination of different elements, so this is a compound. And salt is NaCl, it's a compound as well. Brass is actually a mixture. It's not only iron, it's also some, you have copper inside as well. This is a homogeneous mixture. This is a mixture. Chlorine is an element. It's written as CO2. Air is a mixture of different elements and compounds. For example, in air, you would have a nitrogen, you have oxygen, you have CO2, etc. Let's look at more examples. Which of the following is a mixture? Seawater, yes, that's a mixture. Iron ore, yes. Air, milk. So E is the correct answer. Move on to the next one. How do you classify wine? Apparently, it's uniform throughout. It's made of different components inside. So we do know it's a mixture. It's also homogeneous mixture. C is the correct answer. What is a solution? solution is actually the same as homogeneous mixture. A homogeneous mixture is a solution. A solution is a homogeneous mixture. So next time you run into this, you do know they are exact the same terms. Now let's switch gear and talk about a different topic, which is physical versus chemical properties, or physical change versus chemical change. So what is physical property? Physical property is just the property that can be observed without changing the substance itself. What do you mean without changing the substance itself? That means you don't change the identity. The identity is defined by the composition and or the structure. If you maintain the same composition and the structure, that means the identity is exactly the same. For example, the ability to be boiled for water is a property that is called a physical property. Why? Because before the boiling and after boiling, you retain the same H2O. What about chemical property? Chemical property is the property that can only be observed after you change the identity, or in another word, the composition and or structure of that very thing. For example, the flammability, if you have methane, methane is CH4. When you burn it in the air, it actually changes to different things because it reacts with oxygen and it changes to CO2, carbon dioxide, which is a different thing with different composition and structure, and water. Of course, you can balance this reaction. Then you will have, this is 2, this is 2 as well. This is the balanced reaction. But apparently, the composition and the structure both have changed in this process. So flammability is a chemical property. Chemical property sometimes is also called chemical reactivity. So it's actually equivalent. All right. So for example, iron being rusted. Some students get this wrong, but if you understand what the rusting is, for example, when iron it's rusted, iron is actually Fe. It's rusted, actually it reacts with oxygen. It becomes a different compound, which is iron 3 oxide. Of course, we can balance this. So that's the rusting process. It is a chemical process. So this property to rust is actually a chemical property. So physical change, chemical change is referring to the process to demonstrate those properties. Let's look at some examples. So ice melting is an example of what before and after that, because this is melting, so it's not a property. No, it's not going to be a property. That's a process. So it must be a change. Before and after melting, it's still the same H2O. When you write it, that's H2O. Melting in the original state, that's a solid represented with S, is changed to H2O, but still H2O, notice that? It's in liquid state though. So this is apparently a physical change. Look at another example, which is a chemical property. First, it's a chemical property. The density, you can observe this without changing it, the liquid to different thing. So that's a physical property. Ability of iron to rust. As we explained, this is a chemical property. And what about flammability of the gasoline? So yeah, it's a chemical property. And then reactivity of acids with metals, yes, it's a chemical property. But what are we looking at? Which of the following is not a chemical property? So that's not a chemical property. That's why you pick the A as the correct answer rather than B, C, D. So read the question very carefully. Which of the following is not a chemical property again. Is this exactly the same question? Yes, it is. Yeah, let's skip this one. Yeah. What about physical property? So burning, yeah, that's chemical. Barbecuing the steak, barbecuing the steak. It is actually a chemical property. You think about it this way. Of course, a steak, mostly when you look at that, it's protein. But why don't you eat the steak raw? Because the structure and composition of the steak will hurt our body. So we cannot do it that way. We got to turn it into something that is different type of protein. So that is actually a chemical property, not physical. Of course, you're going to decompose water into different things. Of course, that's chemical. Breaking a piece of glass, yeah, it's still the same composition. It's just existing in different shape. So this is physical. Baking a cake, do you remember? Cake has changed from one thing to a different thing so you can eat it. It's a chemical process. All right, so let's pause for a little bit and summarize what we just learned. So first, what is matter? You do know what matter is. You know the classification of matter into 4 different groups. An element and a compound, which both of which are so-called pure substance. Then you have a homogeneous mixture versus heterogeneous mixture. Both are so-called mixtures. Then we talked about physical property versus chemical property, and physical change versus chemical change. Now let's move on to the next topic. As we just talked about, almost everything that we come in touch with, they are so-called matter. Matter is defined as anything that takes up space and has a mass. So another thing you might come in contact with is actually energy. For example, light is not classified as a matter. It's not a matter because it does not take up space. You turn on the light, it does not take up extra space and has no matter at all. So what is light? Light is actually a type of energy. So light is actually a type of energy. All right, so what is energy? What is exactly energy defined as? Energy is actually the capacity to do work. What is work then? Work is defined as the result of force acting over a distance. That's really important. You can apply force on something, but you have not moved it. You have done no work. There is one important aspect about this energy that is summarized in the law of conservation of energy, which tells you first, energy cannot be created or destroyed. In other words, you can describe it as the total amount of energy is constant. The second thing, however, energy can be changed from one form to another and can also be transferred from one object to another. So let's look at different forms of energy. So the first type of energy is called kinetic energy. Kinetic means it's related to the motion or movement. What is potential energy? Potential energy sometimes is called stored energy, but it's not very accurate. Potential energy is defined as the energy that is associated with its composition or its position. So under this definitions, we have different types of subcategories. For example, electrical energy that is associated with the flow of electrical charge, and thermal energy. Thermal energy is associated with the random motions of atoms. Hey, it's related to motion, so thermal energy is actually a type of kinetic energy. What about chemical energy? Chemical energy is a form of potential energy associated with the position of the particles. For example, every day you drive to class, you actually convert the chemical energy of the petroleum gas into the movement of your car. So the chemical energy, while you're converting this petroleum gas, it turns into carbon dioxide and water. So the identity of petroleum gas has changed. But what's important is when you change the identity, the positions of the atoms have changed. So it is a type of potential energy. One related concept is temperature. Temperature is not a type of energy. Rather, it's an indication or measurement of the thermal energy. The hotter the object, the faster the atoms or molecules that compose it are moving. All right, so let's move on. To indicate the magnitude of energy, we use different units. So you do know the SI unit, or International Standard Unit of energy, is joule. Then one of the common, very commonly used unit for energy is also calorie. Look at, that's lowercase or small c. And the other one is very often used in nutritional or food industry. It's the capital C. Capital C is 1,000 times the little c. So that's quite important. You do remember that, especially if you're in food industry. A lot of times you use the capital C. We have some other units which we are going to skip for this time. All right. Let's go into the details about potential energy and give you one example. So, for example, you have a weight sitting on the top of a building. So this has a lot of potential energy. So if you are higher in elevation, you have a higher potential energy. But if you tip it over, it falls down, the potential energy is being converted into the kinetic energy or the movement of that object. Once it hits the earth, hits the ground, some of the energy is being converted into the thermal energy. Once you notice that, this is actually part of the process of conversion of different forms of energy. Let's follow up of what we talk about with some example questions. So which of the following process has kinetic energy? So when you look at that, a ball is falling, that's moving, a dart is being thrown, okay, a ball is rolling, arrow flying, everything, they are related to the movement or motion of the objects over here. So all above, they are kinetic energy. All right. So we know kinetic is related to movement or motion. Potential is related to the position or composition. All right. Now, let's talk about different kinds of process. One is called exothermic, one is called endothermic. In the exothermic reaction or process, energy is being released. In the endothermic, it's going in, endo. So energy is absorbed. So do you remember one thing, as we just briefly mentioned about temperature? Hopefully you don't confuse temperature with heat. Temperature is the measurement of the thermal energy. It tells you how fast the atoms or molecules are moving inside that sample. The heat is the amount of energy that is being transferred. So they are different. Let's look at one question. So which of the following is true about exo process? So when you look at exo, the reactants possess greater energy than the products. What is exo? Exo, you release energy. So in this process, after you release the energy, your products would have less energy. So A is correct. Energy is released as reaction occurs. So B is also correct. So C is for endo, because it says energy is being absorbed. So both A and B are correct. All right, read the whole thing if you have choices like both A, B, A, C, whatever. All right. Look at another example. Which of the following changes endothermic? Endo means you absorb energy from your surrounding. So water evaporates. Hey, when you try to make water evaporate, you need to add energy to the system. So that's endothermic. The opposite process, water freezes, it releases energy. So it's actually exo for B. Butane gas burns, it releases energy. So this is exo. Steam condenses, condensation process, release energy. The opposite, evaporation. Actually, when you look at that, evaporation is the opposite of condensation. Evaporation is endothermic, and condensation is exothermic. Okay, the freezing, the opposite process for freezing is actually melting. Okay, melting is endothermic, freezing is exothermic. All right, so let's move on. The next topic we are going to talk about is how to convert different temperature scales. We are familiar with one temperature scale, which is Fahrenheit, but we actually use more often Celsius and Kelvin in science. Here's how you interconvert this. You must memorize this or put it on your note card for your exams. So for Kelvin, it's 273.15 plus the Celsius degree. And when you want to convert Celsius with Fahrenheit, so Fahrenheit, well, minus 32 and divided by 1.8. Look at some examples over here. In this example, you are asked to convert Celsius degree to Fahrenheit. We do know one previous equation. Look at the previous screen. Here's how you convert Fahrenheit to Celsius. So let's use this equation to find out the solution. All right, so we do know, as we said, Celsius is actually Fahrenheit minus 32 divided by 1.8. So we know this already. We want to find out Fahrenheit. Fahrenheit, so it will be 1.8 times Celsius degree and plus 32. So you put the numbers in, it would be 1.8 times 42 plus 32. This gives you 107.6 Fahrenheit. So C is the correct answer. Let's do more examples. So you want to convert Celsius degree to Kelvin scale. So Kelvin is Celsius degree plus 273.15. So you substitute 97 degrees C in and 273.15. This gives you 370.15. But you're going to round it off to 370K. So B is the correct answer. So hopefully by now you can convert temperatures in different scales. When temperature changes, actually energy change is involved. So the question would be, how do you calculate these energy changes? So let's look at that. Before we go into the calculation, let's look at a few concepts. So the first one is so-called heat capacity. What is heat capacity? It's asking you the ability to absorb the heat or release the heat, right? So it's defined as, of course, it's the quantity of heat that is required to change the temperature of a given amount of substance by 1 degree. Okay, so when you look at unit, it would be a joule per degree C, because it's the amount of energy per degree C. Specific heat is slightly different. So it's the amount of energy or heat in the form of heat, all right, required to raise the temperature. It's also by 1 degree, but it's only for 1 gram of substance. So it's the energy in joule per gram sample and per degree C. That's why the unit is joule per grams per degree C. Specific heat is usually represented by this symbol in most textbooks, which is CS. Okay, but in our textbook, we use a C to represent it. So it might be confusing if you don't pay attention to the difference over here. In our textbook, we use C to represent a specific heat, but in most other textbooks, they use C to represent heat capacity. So know the difference over here, and we'll move on to the question. The temperature of iron increases more quickly than water when it's heated. So what does it mean? So first thing you got to realize, in this question, it does not mention the amount or the mass of the iron. So apparently, when you look at the previous slide, specific heat involves the amount of substance. So apparently, this is not related to the specific heat. Rather, it's related to the heat capacity. So let's look at this question for one more time. Okay, so iron increase the temperature for iron increases much more quickly than water because it cannot hold that much heat. So for this reason, iron has a smaller heat capacity than water, or in another word, water has a greater heat capacity than iron. So that's what this statement means. It's equivalent of saying iron has a smaller heat capacity than water. For this reason, if you absorb the same amount of heat, the temperature for iron is going to change more quickly than that of water. So how do we calculate the energy change when temperature changes? Here's the equation that should do the calculation. Again, as I mentioned, in different textbooks, specific heat capacity is represented differently. Over here, in our textbook, we use C, but if you see a different representation like a CS, don't be surprised. So how do you memorize this equation? Heat is the mass times specific heat times temperature change. So when you write it, it's written as Q equals MCAT. That's C delta T. So it's like MCAT, right? Or, as I mentioned, many other textbooks actually use CS to represent the specific heat. It would be MCAT in this way. All right. For the temperature change, it's always final minus initial. Never do the opposite. It's final minus initial temperature. In this example, a sample of gallium was originally at 25.0 degrees C. And we know gallium has a melting point of 29.9 degrees C. And then you have 2.5 grams of sample, and it absorbs heat from your hand, and temperature is raised from 25.0 to 29.9 degrees C. So we ask you how much heat is being absorbed in this process. So when you do this calculation, apparently in the very beginning, the temperature is 25 degrees, then it changes to 29 degrees C. So temperature has changed. We do know you should use the Q equals MCAT. All right. So basically what you need to find out is what the mass is, what the specific heat, again, it could be written as a CS, as I just mentioned, and what the change of temperature is. So let's do this. The mass is 2.5 degrees C. The change of temperature, final minus initial, gives you 4.9 degrees C. So put everything together. You substitute the numbers in, 2.5 grams, and specific heat, which is given, and the change of temperature. So you have 4.557 joule, and then you round it off to 4.6 joule. Let's look at another example in the multiple choice form. So let's read the question. It says 0.250 kilogram bar of aluminum at the original temperature of 23.8 degrees C. Then it has 15.5 kilojoule of heat added. So then it's asking you what is the final temperature of the aluminum. It also gives you the specific heat of aluminum. So how do you do the calculation? Apparently, this is the energy change versus the temperature change, right? So when we start, first thing you got to realize, in this equation, Q equals MCAT, M times C or CS, and delta T. Look at the units. The mass should be in unit of grams, because when you look at the specific heat, look at the unit over here. To cancel out the mass unit with the aluminum, you must have grams inside rather than kilograms. So because the unit has joule per grams per degree C. So do remember the mass should be converted from kilogram to grams. All right. And the heat, which is given over here, it's in kilojoule, but here it should be joule, because when you write everything, unit multiply this, multiply degree C. So grams cancel out, and degree C cancel out. You will end up with joule rather than kilojoule. So let's substitute all the numbers in. You will have, look at this, 15.5 kilojoule. So it's times 1,000 joule equals, what is M? M is 0.250 kilogram, but again, you got to convert it to grams. Times specific heat, and then put the joule per grams per degree C, and you have the unit, correct. Then you have final minus initial temperature. So that's my T final minus my initial, which is 23.8 degrees C. All right. So you solve for TF. So what is TF? It turns out TF is 92.5 degrees C. So C is the correct answer. All right. So that's it for today. Have a good day.